how do you find the order of complexity for eigen decomposition? I said it was order n cube. I didn't find the order of complexity, I only stated it. Okay, so why is it order n cube is not something that I've proven here. It is something that you do in a linear algebra class. Okay, it's a standard result like Gram-Schmidt process. So we are not proving it. In the affine space result of the expanding subspace theorem, is the x naught only a general vector or a specific x naught? The x naught that we have taken so far as the starting point of the CG method is completely general. There is nothing special about it. Okay, so you can take it to be whatever favorite point you want. What people, if you don't have any a priori knowledge about it, you would initialize it by a random variable. Okay. So there's nothing special about it. None of the results depend on it, that it being something special. The only thing special is about the starting. Have we done that yet? The starting conjugate vector? No, right? Okay, we'll come to that. Is the conjugate direction method and the conjugate gradient method valid only for solving Ax equal to b when A is symmetric positive definite? It's a very small subset of problem. So answer is it only for solving Ax equal to b when A is symmetric positive definite? Yes, no? Should be? Answer is no. I think we did this in class. What if I give you a which is not positive definite and I want to use CG method? What do I do? Transformation. What transformation? At the back there? Or do we have to go back to something like gradient descent? Anyone? Come on. If the eigenvalues are? But then you have changed the problem, no? If I change the signs of the eigenvalues, I make it, I change the problem itself. So this is the problem statement. I want to do conjugate gradient method. You have seen that in whatever we have done, we have critically depended on the fact that A is positive definite, symmetric positive definite. But now I give you A which is not. What do we do? Any idea? I'm surprised because I derived this, I thought, the last time around, in fact. No, that is in a quadratic form, the skew symmetric part doesn't contribute, right? Pre-multiply by A transpose. If I left multiply by A transpose, what do I get? A transpose AX is equal to A transpose B. What is this A transpose A matrix? Is it symmetric? Is it positive definite? It's positive semi-definite. Why? Because it can have some eigenvalues which are 0. Right? So as long as this is positive definite, right, you can see that X transpose A transpose AX. What is this? This is norm of AX squared, right? If A is full rank, then this norm can be 0 only when X is 0. In other words, for non-zero X, this cannot go to 0, right? So only when X is equal to 0. So to solve, so as long as you tell me this is full rank, I can do this, right? I can solve this system of equations. The solution to this is the same as the solution to X equal to B. What was the problem with this, slight disadvantage of doing this? We are not inverting it. Remember, in solving in the conjugate gradient method, we can write formally I can write the solution is equal to A inverse B. This is formally the solution, but do I ever evaluate A inverse in whatever we do? We never evaluate A inverse. So similarly, we will never evaluate A transpose A inverse. It's just symbolically writing it as a solution, but we will never do it because it's computationally very expensive to do it. Okay, so similarly here we won't do it. But what is the slight disadvantage of going this way? The condition number, right? The condition number of A transpose A is square of the condition number of A, right? So the in the subsequent few lectures we will see what role condition number plays. Okay, so this is, but I mean, if you're telling me that A is not symmetric, I have no option. I have to go through this route. Okay, so there is some cost to be paid. So it's not, so the conjugate gradient method is not very restrictive. It can solve any Ax equal to B. Of course, it makes sense to solve Ax equal to B only when A is full rank. So it's not very restrictive. Okay.